So 7.5 again. And if you think about it, really yesterday we did solve a system of inequalities graphically, the last one. No really words that went with it, but that's where these problems come from. In business, there's a lot behind this that an accountant has to figure out so that they can get the constraints, the objective function, and be able to tell the boss where they should be working at, what they should be providing, how much they should be providing. So we are here. I'm going to do a couple word problems, which means we're writing the constraints, we're writing the objective function, we're graphing, and we're trying to figure out the maximum or the minimum, whatever it is they want from us. So, purchasing fertilizer, hopefully for farming, not for blowing things up. So, purchasing fertilizer. Johnson's Produce is purchasing fertilizer with two nutrients, nitrogen, with an N, and P for phosphorus. And they did that because they wanted to shorten up this problem a little bit. They need at least 180 units of nitrogen and 90 units of phosphorus. Their supplier has two brands of fertilizer for them to buy. Brand A costs $10 a bag and has 4 units of nitrogen and 1 of phosphorus. Brand B costs $5 a bag and has 1 unit of each ingredient. Johnson's Produce can pay at most $800 for the fertilizer. How many bags of each brand should be purchased to minimize costs? It's a lot of information. So what you have to do is, again, if you go through and you kind of grab, hey, this sounds like a total, that will help you figure out what you need for your equations. And the first thing I saw here was they need at least 180 units of nitrogen. So that's telling me something has to be greater than or equal to 180. And that is one of the constraints. Now that was about nitrogen. And I know there are two brands here, but I'm going to use X and Y versus A and B. And so I go through and I'm trying to find things about nitrogen, because if this is my total, and that total is about nitrogen, my whole equation or inequality needs to be about nitrogen. So brand A, $10 a bag, 4 units of nitrogen. So I'm going to have X stand for my brand A here, and I suppose I ought to take the time to write that down somewhere. But X will be brand A and Y will be brand B. And then we need to find out something about nitrogen from brand B. And it says brand B costs $5 a bag and has 1 unit of each of the 2 nutrients. So 1Y. Now, that wasn't the only total. They need at least 180 units of nitrogen and 90 units of phosphorus. Now, I'm going to switch colors because, again, I want a color code for this whole thing as we go through it. So they need greater than or equal to 90. And this is the phosphorus. So I go back to the information. Brand A, blah, 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 1 unit of phosphorus. And brand B, again, said 1 unit of each nutrient, like so. But there was another constraint in there, and that other constraint had to do with money. Johnson's Produce can pay at most $800 for the fertilizer. So that has to be a less than or equal to, change colors again, and now we're going to be talking about the price. So I go back and see that brand A was $10 a bag, and brand B was $5 a bag. Now, we read through it quick again and realize, well, we used the 180, the 90, $10 a bag, 4 units, 1 unit. Brand B, $5 a bag. We used that. 1 of each nutrient, pays at most $800 for the fertilizer. Bless you. And those are the big ones. Now, we still have to do the 2 that I call the obligatory constraints. We're obligated to put these down, even though it would seem like it's totally understood. I mean, you can't buy a negative amount of fertilizer. You can't do that. So, while it may not help us a lot with our graphing or anything, we do need to put down that x needs to be greater than or equal to 0, and y needs to be greater than or equal to 0. And I ran out of colors, so hopefully you can still see that, Google Meters. I know the green is tough. There it is. So now, we have a lot of work to do. I mean, we need to get this graphed, and we start thinking, well, I need an objective function. So the objective function is usually found in the last sentence of the word problems. How many bags of each brand should be purchased to minimize cost? So I realized, well, I already used cost in my constraints. Doesn't matter. It's also going to be what's key for your objective function. And remember, this one's an equation. And we know brand A was 10 bucks a bag, and brand B was $5 a bag. So once we can get everything graphed, then we can go back to that objective function and tell them what's going to minimize the costs. But to graph it, we need to have an idea of what kind of numbers we're looking at. So again, color code. I'm going to go ahead and grab the red so I can work on 4x plus y equals 180, because I need a boundary line. And since this is in standard form, and really it is helpful anyway when trying to figure out what you could use for your units as you're going up the sides here, it'd be better to find the zeros. So if we have a 0 of brand A, then we're going to need 180 bags of brand B. And if we don't get any of brand B, so we cover up the Y, now we need 180 divided by 4, which is going to be 45. So that's helpful. And right now I'm thinking, yeah, I might have to go out to 200 on each one of these, but I haven't done the other ones yet. So changing again. Next one was x plus y equals 90. Love that one for finding the zeros. Very straightforward. If you don't get any of one, you need 90 of the other. So 0, 90, and 90, 0. And then I'll change colors one more time. For my 10x plus 5y equals 800. All right, so if we don't get any of brand A, so this is gone, we need 800 divided by 5. And that's 160. And if we don't get any of the brand B, we've got 800 divided by 10, which is 80. Now, I would like to keep the units the same going each way, but it looks like we've got a major difference here. On our y-axis, we have to go to 180, 90, and 160, so definitely going to about 200. And this is 20 by 20. That'll help you figure out here that we should go by tens. And then on the other axis, we only have on the x-axis 45, 90, and 80. So maybe we'll just go to 100 on that one. The more we can stretch it out, the easier it's going to be to see those intersections. So we're going to make this all first quadrant. That is not a straight line. And label our y-axis up to 200, going by tens, but again, don't label every little square or you just can't read anything anyway. So let's maybe go with 1, 2, 3, 4, 5 and put 50 up there. But on the x's, spread it out a little more. So each one of these, we're going to go by 5. So these I'm just going to label 20, 40, 60, 80, 100. However you label it is fine, just so that we're going by fives. And now we start graphing. So we know we're in first quadrant, but color code, this is really important because we're going to have to find these intersections later. So color code. For my red one up here, I've got my 0180. And 450. But then I remember this one said at least, so it has to be greater than or equal to 180. So this is kind of weird. We're going to have to go shading outward. Now I'm not putting arrows on this one because you can't have a negative amount of bags. Don't forget to change your colors as you go to the next one. So the next one was our 090 and 90. And that one again was an at least, so we'd like to have more, which means we're shading out this direction. And the last one here, which is the blue that always wants to give me trouble. We've got our 0160 and 80. But that one was money. And nobody has an unlimited supply of money. So that one does not shade outward. That's going to shade back towards 00. Some are pretty close. We'd say, yeah, they have close to an unlimited amount of money, but they don't. There's a limit for everybody. And then, like we did yesterday, I would probably just use my other color to show, yeah, first quadrant. Got it all right there. Now we're not done yet, and we're much closer than we were before, but I have to look for, on mine, the blue, the red, and the black. And I realize that's forming this triangle in here. Now I need the vertices. I don't draw straight lines freehand. I know that. And in fact, if you're doing this in business, you're not going to go by what you've drawn anyway. You're going to go by the math. And yesterday we found the intersections of all of these using algebra. And this one actually isn't too bad using algebra 4, but we're supposed to figure out how to do this with our calculator as well again. So we're going to go ahead and get all of these. We're going to color code them and put them into that y equals mx plus b form. So again, try to have everything in the same color so that you know which line it is we're trying to find with which line. Did anybody use like a straight edge when they were drawing theirs? We need to see if anybody gets something even close to what we find here when we use the graphing calculator. So, I've decided I would like to do that one first. And this one up here is where blue and red intersect. So I'm going to have to use these two equations down here and find out where they hit each other. if I can keep them so I can see them. Y equals negative 4x plus 180 and negative 2x plus 160. But I'm going to have to change my window. You know, and I want my window to match what I have here. So for my x's, we had 0 to 100. And for the y's, 0 to 200. Because then I can visually see, yep, it was that upper left-hand quarter that I wanted to see, and I see they're hitting each other right there. So, second trace, number 5, enter, enter, enter. 10, 140. So these are the vertices that we're looking for. Well, 2 more to go. This is black and red for me. So I'm going to have to use the negative 4x plus 180, but I want to see where that intersects negative x plus 90. Now I'm not going to take the other one out, because I know I'm going to need it again. But I'm going to turn it off. So that was the one that had the y-intercept of 160. So all I have to do is go back to where it says equals and just hit enter. And that one gets turned off until I turn it back on again. There it is. Second trace, number 5, bing, bang, boom, 3060. One more intersection, blue with black. So I'll have to leave these 2 on and deactivate the one that has the plus 180 on it this time. And find that intersection. 7020. Now at this point, you might have already forgotten, what is it we're trying to do again? Because that's a lot, you know, you go through a lot of math to get to this point. But it's all about that objective function. So I have to take these vertices and put them into, way back up here, we said our objective function was c equals 10x plus 5y. So let's see what we get. So we would have 10 times 10 is 100, 5 times 140. Oops, get out of the graphing. So plus 100 would be 800. 30 and 60. So we'd get 300 and 300. Grand total is 600. Then 70 and 20, so 700 plus 100 is 800. And we remember we were supposed to minimize cost. Well, that's going to be the 600. That's the lowest one there. So, to minimize cost. I forget, were they producing or were they buying? They are buying. So they should purchase 30 bags of brand A. Not Brad A, brand A. And 60 bags of brand B. And they'll have it. All right, so this one showed us, like it says, example 7 provides an example of a bounded region. We actually had a figure inside there that was our feasible region. And that means that we can find both the maximum and the minimum. Now, we don't have the equation that they would want us to use to maximize profit or anything like that. This one was just about the cost. But that is not the case for all linear programming problems, and we're going to see that in the next one. So here it is, minimizing operating cost. Ganza Manufacturing has 2 factories that produce 3 grades of paper: low grade, medium grade, and high grade. It needs to supply 24 tons of low grade, 6 tons of medium grade, and 30 tons of high grade paper. Factory A produces 8 tons of low grade, 1 ton of medium grade, 2 tons of high grade paper daily. Costs $2,000 per day to operate. Factory B produces 2 tons of low grade, 1 ton of medium grade, and 8 tons of high grade paper daily, and costs $4,000 per day to operate. How many days should each factory operate to fill the orders at minimum cost? Wowzers. Again, lots and lots of stuff going on there. So I go back and I look for totals. They need to supply 24 tons of low grade. So, what does that mean? Do we want it to be equal to 24? Well, they do, but they have to have at least 24 or they're not going to be able to fill the orders. So it could be greater than or equal to the 24 tons. Now that was about low grade. So everything in that inequality needs to be about the low grade. So let's see. What did it say about the different factories here? Factory 8 produces 8 tons of low grade. So I'll have XB, Factory A, and Y, Factory B. So let's see, Factory B, 2 tons of low grade. So there's everything about the low graders. Changing colors. Needs to supply 24 tons of low grade, 6 tons of medium grade. Again, 6 tons would be perfect, but they're probably going to end up with a little more than that. So let's go to medium grade. Factory A, 1 ton of medium grade. Factory B, 1 ton of medium grade. So that was the MG. And 30 tons of high grade paper. So Factory A produces 2 tons of high grade daily, and Factory B, 8 tons. Wow. Of high grade paper daily. So far, so good. Now, how many days should each factory operate to fill the orders at minimum cost? So let's make sure we've used everything up to this point, up to where we need the objective function. We've got the 24, the 6, and the 30. The 8, the 1, and the 2. We're going to minimize costs, so we'll be using as an objective function C equals, Factory A is $2,000 per day to operate, and B is $4,000 per day. I don't think there's any other numbers up there for us. We've got them all. But we need the obligatory constraints, which are X has to be greater than or equal to 0, and Y has to be greater than or equal to 0. And we start the process again. So we need to know what we should use for our intervals for our X's and our Y's. So go back to color coding again. Whoops, boundary lines, we want to know when they're equal. And find the zeros. find the intercepts. I like that one. The little black one was nice and easy. Then we go to the blue. Not quite so pretty, huh? That'll be 38ths. So 15/4. And then 15/0. Oh, I forgot the middle one. It's a good thing I color coded. Because I was thinking, well, that one will be super easy too at 0, 6, and 6, 0. Well, we have 0, 12. Then we have a 15, 0. Well, we can just make our little blocks go by 1, so we'll be able to go out to 20 in both directions, and that should take care of it. Oops. Oh, some of you are already putting your lines on. All right, go for it. Once it looks like everybody has them all on there, we'll make some really big dots on our vertices this time. Because when you have these unbounded feasible regions, it's a little harder sometimes to make out where are we looking for? What are those spots? All right, so we have, and I don't want to go right over the top of my lines because I'm going to need that to find my intersections, but right here is definitely a vertex for this weird unbounded feasible region we have. It's not going to be a figure this time. And then we have another one right here, and right here, because it has to be all three colors that we see. And I know we've got that x is greater than or equal to 0 and y is greater than or equal to 0, but that's all first quadrant. So again, we need to figure out where those are going to be, which is so helpful to have the graphing calculator for this. So let's just get these solved for y so we can pop them in. Again, keep them color-coded. Now, two of the vertices we can get without the calculator, and that's because they ended up being our x and y intercepts as we go through this graph. We've got the black graph right here up at the top, and that was going to be 0, 12, so that's one of the vertices. And then the blue out here at 15, 0. And then we just need to start punching stuff in. So I'll go from left to right as we would read. This one is black versus red. So I want my black and my red equations. You'll have to color code with yours. And I might as well punch in the other one while I'm here, since I know I'm going to have to use it anyway. And then I can just turn it off for the time being. Now, we went from 0 to 20 on both of our axes this time, so we probably want to make that change so things are a little easier to see. And yeah, that's where they hit each other, so let's find out where it is. That is at 2, 4. All right, so we've got this one and this one. The next one for me is going to be red hits blue. So the one with the fractions in it and the one with the 6. There they are. Second trace, number 5. Enter, enter, enter. 3, 3. There's that green again. So do we get them all? 1, 2, 3, 4. Got them. Now we just have to go back and pull that objective function. C equals 2000x plus 4000y. And plop these in. All right, so 0 of factory A and 12 of factory Y will give us, I'll punch it in, although it's kind of silly. $48,000. $15 of factory A, again, kind of silly, but 30,000. 2 and 4. So 2 times 2,000 would be 4,000. And then we'd have 16,000. So 4,000 and 16,000 would be 20,000. And then 3 and 3, 6,000 and 12,000 for 18,000 as a total. Is this maximize or minimize? Yeah, of course it was, because it was cost, right? So we would go with the 3 and 3. So 3 days of factory A and 3 days of factory B. Now again, it probably is going to produce a surplus of one of the papers, but that's okay. They just have to be able to fill all of their orders. And the reason I'm bringing that up is if we go back up here and we put a 3 and a 3 into the low grade paper, we've got 24 and 6, so they're going to produce 30 tons, which is too much, but they'll be able to meet their orders. A 3 and a 3 here would give them exactly the 6 that they needed. A 3 and a 3 here, again, would give them exactly what they needed. But they're going to have a little bit too much of this low-grade paper. They don't care. They have to be able to fill their orders. So that's what's important. Well, now I wish I would have stopped and asked some questions. I was so worried about time today. But every time I looked out, you guys were busy graphing and everything. Any questions about anything that we did today? It looked like you had this. You feeling like you got this? All right, good. And yeah, I'm going to hand sanitize and get you some big graph paper here. I was just thinking about how long each one of those takes. And people always worry about this showing up on the test. It's like we can't put more than pieces of this on a test, or the whole test would be about linear programming. So you'll see stuff on the test about it, but I wouldn't plan on having to do the whole thing. It's just too much. It takes too much time. They're great problems, but just takes a lot of time.